Okay, hi everyone. So today we have the PhD seminar of Rotem. So Rotem is one of the Technion veterans. We are working together for like 13 years.
Well, maybe.
What, 12? I think.
Oh,
Yeah, so I don't know what will happen now. Maybe I need to retire. So you will see she did a quite diverse work during a PhD.
thank you. Okay, so hi everyone. I'm going to talk about my research about enhancing computer performance with memristive memory processing unit. It's not working now, the remote.
Oh, we got the idea.
Okay, we can finish. What do I do?
Green.
Oh, okay, fix it. Okay. So I guess all of you know that the performance of computers today are limited by the structure of the computers today. That the processor is processing the data and the memory is storing the data. And all of you are familiar with the von Neumann bottleneck, which is the performance bottleneck is called the memory wall, and there is also an energy bottleneck. And our group is trying to solve it by using processing in memory or PIM. And we're trying to process using the actual memory cells of the memory. So there were many students who are working on it or worked on it in the past, and I'm going to show you what I did inside of this entire project. So how can it be done? Using an element that is called a memristor. It can be implemented using many technologies, but in the scope of this talk is I'm going to use it just as a digital element. How does it work? It stores the data by resistance. So if we apply a voltage in a certain polarity, then the resistance decreases. If we apply the voltage in the opposite polarity, the resistance increases. And then we can define that a low resistance is a logical one, and the high resistance is a logical one. Okay. So what's special about these elements is that in addition to storing data inside of the memristors, we can also perform a logic gate, such as an OR gate. How does it work? We have three memristors. Two have the input of the logic gate, and the third one has the output, where the initial state of the memristors, of the two input memristors, represents the input of the logic gate. And we're doing two steps. The first is to initialize the output memristor to a low resistance. Then the second step is to get the output result, which the resistance represents the output of the logical gate according to the inputs. So this is the NOR gate. And what's special about the NOR gate is that it can be implemented using three memristors in the same row of the memory. It also can be executed with the three memristors in the same column, so it's symmetric. And also you can see that the voltages that are applied to the columns are applied to the entire columns, so we can execute a gate in each row in parallel. And since NOR is a complete logic function, we can compute any computation that we want executing a sequence of NOR operations. And also because we have a large parallelism of the same operation, then it's good for CMD, single instruction multiple data operations. And also we have the flexibility to decide if we want some of the rows not to be executed by applying a voltage and be isolated to them. So we'll see a small example of how we execute the function using the NORs. If we want to perform really simple operations such as OR over these inputs, and OR is two NORs, A NOR B and then a NOT. The NOT is a single input NOR. First, we initialize the output memristors as we saw before. Then we perform the first NOR operation, we receive the A nor B in each row, and then we get the final result. And it took 3 steps to do it. The area is 4n cells if we also include the inputs, and the energy is 4n if we include also the initialization cells. It's a small thing. Okay, so what's special about it is that the latency of the vector is independent of n. So it's good for improving the throughput, as we will see soon. Okay, so everyone are suggesting to add memristive memory, or already are adding memristive memory to the memory hierarchy. And what our group suggests is to add an MMPU instead, a memristive memory processing unit, which can both store and compute. How is it performed? If we have the data inside the memory, the CPU sends an instruction, the controller of the MPU divides it into NOR operations, and then these operations are sent to the memory and are converted to voltages that are applied on the rows and the columns of the memory, according to the operation that we want to do. And then we get the result inside the memory without any need to transfer the data outside of the memory, only the instructions. So there are a lot of aspects to the MMPU. First, there are all the low-level stuff, which are the memory design, the logic, the periphery, the controller, the interfaces, programming model and software, and the applications. And my first 2 works were on the MMPU controller to implement an efficient controller, and they're both application videos. And then my 3rd work is DarkBeam, which is application specific it's an accelerator for DNA sequences. So I'm going to start with these 2 works and then to go to the 4. Okay, so I'll start with simple and simpler, which are general purpose MMPU controllers. There are 2 approaches to implement the controller. First, it's to do it manually, and then it's fixed, and it's might be better for some applications. And what I try to do is to do something that will do it automatically. It will be flexible. It will be better for general purpose, and that's simple and simpler. What does this controller need to do? First, it needs to control regular memory operations, and also to perform or control optimized logic operations. And how are we going to do it? How are we going to optimize it? By using the parallelism. And what are we going to optimize? We're going to optimize the performance, area, or energy. And the performance, it's both in terms of latency and throughput, where latency is the simple work and throughput is the simpler work. But why can't we just optimize it the same as the CMOS? When we synthesize the CMOS, then we want to improve the performance, energy, and area by reducing the number of gates. So for example, if this is the circuit we have, we will synthesize it, and this is what we'll get. But with memory stores, it's not the same thing. And why? Because if we reduce the number of gates, it's not enough, and the mapping also determines the possible parallelism. For example, here in this example, we have 2 gates which are aligned, so we can execute it in the same step, in one step. But here we have 2 gates which are not aligned, so we can execute it on the same cycle, and we need 2 steps for it. So simple and simpler both perform both synthesis and mapping. Where simple improves the latency, and it uses both rows and columns for a single instance of the function f. It uses optimization problems, and it's not reusing cells. And simpler improves the throughput. It has a single instance in each row, so we have many instances of the function f, which are executed in parallel. It uses heuristics, and it reuses cells. So we'll start with simple, which improves the latency. Okay, so this is the flow of simple. As I said, it performs synthesis and performs mapping into separate stages. So first, we have a logic function that we want to execute. We also define which are the gates that we can use, for example, nor and not. And then using the synthesis tool, we will get the optimized nor and not netlist.
Okay.
So for example, here, we have a 1-bit full adder, and the synthesis tool gives us the nor and not netlist. So that was simple, and now we will see the mapping, which is more complex. So we get the netlist. We also get the constraints for the optimization problem, and then we will get the mapping. What is the problem? First, the variables that we have is for every gate j, we have the inputs of the gate, the output of the gate, and we need to know the locations of them, meaning that we need to know in which row and which column each input and output. And also we need to know the clock cycle, which is gate was executed. What is the optimization problem? We will look at all the T's, all the clock cycle that each gate was executed. We will take the maximum of them all because this represents the time that it took to execute the entire circuit. And then we will minimize it because we want to minimize the latency. Okay, what are the constraints? The first one is the location constraint, and it's pretty obvious. We want all the inputs and output to be located inside the memristive memory and not outside it. The next constraint is that if we have an output of gate K, for example, this one, and then we execute another gate, we can execute it in a separate cell, but we can't execute it in the same cell. And this means that we cannot reuse cells, as I said before. Okay, third constraint is that all three memory stores has to be in the same row or in the same column. Another constraint is that if we have two gates that are executed in parallel, then the T of both of them has to be similar because they're executed together, and also there has to be a line in the inputs and a line in the output, the same here. And the final constraint is related to the connection. If we have two gates that are connected to each other, then the cell that the output of the first gate has to be the same cell that the input of the second gate. Okay, so that was the optimization problem.
So what about space consumption? You minimize time, but what about space?
It's a different, it's not the same optimization. It's a different.
At the same time, I want not to
Yeah.
consume a huge array. So
I agree, but this work only.
It's in the next one.
Sorry. Yeah, we'll talk about it in the next one. We thought about improving it and then also talking about energy and area, but then we shifted it to a different approach. It's the next work, and we'll talk about there. And there we minimize the area. Okay, so then we got the spatial execution sequence. So for example, for the 1-bit full adder, this is the sequence. In the first cycle, we have 4 gates that are executed in parallel. Then in the next cycle, we have 1 gate, etc. And then we have the entire execution of all of the 1-bit full adder inside the memory using 3 columns and 13 rows. So as you see, it's both it uses both magic rows and magic nor that is implemented in rows and nor that is implemented in columns. Okay, if we look at the results, then we can see that we got a 1.87x improvement over the original netlist in terms of the latency or number of computation steps. And compared to previous works, we got 1.55. And you can see more results in the paper. Okay, so now we're going to talk about simpler that improves the throughput. And as I said, we changed, we understood that this is better and this is more important. Yeah.
The optimization, was there any specific smart algorithm, any special idea or brute force trying, or AI, what was it?
Well, I just used the optimization. I don't remember which tool I used, but
It's an existing optimization tool that you gave constraints.
Yeah. Do I have a clock here? No, right? Okay. So we'll talk about simpler. Simpler involves throughput, where we have an instance of the function, a different instance in each row, and then we can execute it in parallel. And the throughput is the number of instances, R in this example, divided by the length of a single instance. And so the flow is similar, the synthesis tool is the same, and we're going to focus on the mapping tool that takes the netlist, knows the array size, and maps it to a single row. Okay, but why do we even need it? The naive, let's look at the naive mapping and understand why we need a more complex mapping. So we can just take the netlist, divide it into levels, where in each level the gates are not dependent on each other. And then we can just execute it level after level, and inside a level we can choose whatever order it doesn't matter. If we have the order that I just showed you, assuming that we have enough area in the crossbar, these are the inputs, and these are the places that we're going to execute the outputs. So we can execute the gates one after the other in all of the columns until we finish all of the gates. And it took us 12 clock cycles, the same as the number of gates, and the throughput is n over 12. But what happens when we don't have enough columns, which what usually happens if we want to execute the code?
Is it n over 12 because you cannot pipeline? If I have many, you're talking about throughput, so
Yeah, I can't, each of them takes a clock cycle, I can't do it in parallel, if that's what you mean.
and you cannot operate the first column for the next data. But
No, you can like,
You can?
no, you can't.
You cannot, okay. So that's the.
You finish the first one and then,
No, but all of them are done in parallel.
yeah, but you are doing.
No,
all
the rows,
instances
the rows
in
are in
parallel.
parallel. The same understand.
The column is in parallel, but then the entire column is in parallel, but you can parallel different columns.
Yes, okay.
So if I don't have enough columns, then I will execute the gates that I have enough space for them. It will take 7 cycles for 7 columns. Now I don't have enough place anymore, so I will see which gates are not needed anymore. These are not needed because their outputs are used by the 5th gate and 6th gate, which were already executed. So I can initialize them in a single cycle, and then I can execute 3 more gates. Again, I don't have enough place. I will check again which I can initialize. I will initialize 2 more because this is what I need. And then I can finish in 14 cycles because I had 12 cycles for executing the gates and 2 more for initializations. And the throughput is n over 14 in this case. So we need an algorithm for efficient mapping into a limited size row using reusing cells. And this is our simpler tool. Okay, so how are we doing it? First, we perform a reduction from a netlist to a DAG, a direct acyclic graph, where these are the roots of the graph, and these are the leaves of the graph. And the execution order that I choose, it influences 2 things. Both how many cells are enough for execution and also how many initialization cycles I need for it. So we're using a DFS algorithm that we're inserting V to the execution if either V is a leaf or if all the children of V are in the sequence. But if, for example, we arrive to this gate 6, where should we go first, to the right or to the left? Let's see both examples. If we start to the left, we will go to gate 1. First, we enter gate 1 to the execution order, then gate 2, then gate 5. At this point, we have 3 cells, and we don't need gate 1 and gate 2 anymore because we finished with them, so we can release these cells. Now we go to gate 4 and finally to gate 6. So we need 3 cells for executing this. But what happens if we go to the right first? we will enter gate 4 to the execution order, then gate 2, gate 1, gate 5, and only at this point we can free gate 2 and gate 1 where we need 4 cells for it. So in the second example, we need 4 cells. So what is the result? The conclusion is that we need to traverse a subtree who needs more cells first. So to do that, we estimated the cell usage value for each subtree. How do we determine the CU value? If if the CU is 1, or else we take the maximum of the CU of the children plus the location of the child minus 1. And the location of the child is all the children are sorted by the descending order of their CU values. So this is what we'll get. And we order them by the values, and then we get also this value. So the number of the CU value of each gate, it represents the number of cells, or the CU plus 1 represents the number of cells that are necessary to execute the subtree. But the thing is that it's accurate only for trees, and we have a DAG. So for a DAG, it's only an estimation. But you can look in the paper, we did estimation, we checked, and we saw that it's good enough. Okay, so back to the how we map to a limited size array. We determine the execution order according to the CU value, as you see here. So this is the order that we chose. Now you can see that we have 9 columns, including the input. So we have 6 columns for execution. We execute the 6 first gates, then we free the ones that are not needed anymore. We execute the next 3, and so on. And it takes 14 cycles to do it with 9 columns. And actually, if you want to do it with minimum number of columns, we can reduce even 1 more, but then it will take 16 cycles. So we'll need, in this case, we will need 4 initialization steps. Okay. So if we look at the area reduction, it's the area relative to unrestricted area. So we can see here in the average that the area was decreased by 5.8x at the cost of a 6.2 latency degradation. And if we allowed to add a few more cells, the maximum of 5% or 10 cells, and we can see that the area decrease is quite similar, but the latency overhead was reduced to 2.3%. And this is because when we use the minimum area, sometimes we reach a point that we initialize only 1 cell and then we use it, and then we initialize it again and then we use it, and then it just increases the latency. If we compare it to previous work, then we can see that on average we improved about 20-something weeks, both the throughput and the area compression and the area efficiency. And at the cost, like the latency is quite similar to the previous work. And again, more results in the paper. Okay. So my last work is the DARPIM, which is an accelerator for DNA sequencing. But why do we need an accelerator for DNA sequencing? The world today is going into an era of personalized medicine. Why? Because we know that if different people have the same diagnosis, they respond differently to treatment. So the goal is to adjust the treatment by the DNA of the person. And how can we do that? By using DNA sequencing. What is DNA sequencing? First, the DNA is two long strands with the bases, which are in a shape of helix. And they have bases, and the DNA sequencing is to determine the exact sequence of these bases. So we need a rapid and accurate sequencing in order to have a personalized medicine. what is the sequence process? First, we have a genomic sample, which we said it looks like a helix, but actually this is what it looks like a ball of wool. And if we want to sequence it, it's pretty hard. Why? Because we enter it into a sequencing machine, and this machine chops it into small pieces and extracts small strings out of it, which are called reads. Now, these reads, we don't know where they came from, because as I said, this is what the DNA looks like in our cells. So we need to understand each read where it came from, and this is called the read mapping process. And after the read mapping, we can have the whole genome. And this read mapping is the bottleneck of the entire DNA sequencing process. What are the challenges of the read mapping process? The human genome has 3.2 billion bases, and we have hundreds of millions of short reads, which are 50 to 300 bases each. And we need to understand each read where it came from. How are we going to do that? And luckily, the genetic similarity between different humans is 99.9%. So we can use a reference genome, which is kind of the average genome of every human being. And then we can use it to understand where each read came from. How are we doing it? Using the reference genome. For example, here we get the reads. We need to map each of them to the location and to the best location. What is the best location? We're using approximate string matching algorithms. And why approximate? Because each genome is similar, but not exactly the same. And we need to allow a few changes. So for example, the first read, we take it, we compare it to all of the possible locations, and then we need to understand which is the best location. And the same we do with all other reads. And after that, we can extract the whole gem, the whole sample gem. Okay, what is the read mapping process? On offline, we're taking the reference genome, and we're doing something that is called indexing. We take substrings from the reference genome, which are called minimizers, and we save a table for each minimizers. What are the locations that it appears in the reference? During runtime, we receive the reads. Then we perform seeding, where we take a read, we find its minimizers, we check which locations in the reference these minimizers appear. And these are our potential locations, meaning these are the locations that probably the read came from. Then we continue with these potential locations to the next stage, which is filtering. We take all the locations and we filter them just to leave us with less locations. And finally, the read alignment step, which is the most computationally expensive step, where we do a dynamic programming algorithm to compare the read and the reference segment at the chosen location. And then we can see how similar this read to this location. And after we check all the locations, we can choose the best location out of them and to get the whole gem. Now, if we look at the conventional accelerators, then we see that everyone previously tried to accelerate a single step of the process. But the problem is, and what they might have missed, is that if we look at the inputs, we can see that it's about 16 gigabytes of reads in the genome, reference genome. But if we look at the data that is transferred between the different the stages, then it's 2 orders of magnitude larger. Meaning that if we accelerate this stage and then we write the results to the memory, and then we need to read it again in order to perform the next stage, then the data movement inside our system still limits. So the solution is to perform all the steps inside the same memory units. And this is what Dartbeam does. It executes all the stages of grid mapping within the same memristive crossbar array. And it eliminates the need to transfer data between the different stages. Okay, so this is Dartbeam architecture. We have 32 chips, 512 banks per chip, 512 crossbars per bank. Each crossbar has 256 rows and 1024 columns. So it's a total of 32 kilobytes. And the entire system has a 256 gigabytes. And we also have in each chip 4 RISC-Vs, which their role is to perform the read alignment of low frequency minimizers, meaning that they do some of the computation, but only 0.16% of the computations. So most of the computations are done in the crossbars, but it helps us to reduce the total needed area of the system.
What's the problem with low frequency minimizers?
Sorry?
What's special in low frequency?
I'm not explaining it here. I'll say a sentence about it in a second for you. Okay. So what are the stages of Dartbeam? We will go one step after the other and see how it is executed in Dartbeam. So we'll start with the indexing. As I said, the conventional indexing stores the table inside the memory, and it requires many loads of reference segments later during runtime. So we are not doing it. What we are doing is we assign each crossbar to be responsible for a certain minimizer. And we save the actual reference segments inside the memory crossbars. Instead of saving the locations as the conventional approach, we save the actual reference segments. And I'll say it here what you asked. If we're saving it inside the crossbars, if we have a location minimizer with low latency, then we save the entire crossbar for them. And we are not using the entire crossbar, we are using only, like if we have only one minimizer that appears only one time in the reference, then we'll have a crossbar, an entire crossbar with only one. And there are many minimizers like that. Okay, next, the seeding stage. In conventional seeding, then we receive the read, we find its minimizers, then we find the potential locations. We're doing something different. In each crossbar, we will have a reads FIFO, and then we can enter each read to the relevant crossbar according to its minimizers. So we take each read, we find its minimizers, and then we enter it to the relevant reads FIFO. How we do it? We send the reads to all of the, we transfer it to everyone, to all of the crossbars, and each crossbar knows if it's my minimizer or not, and then if it's minimized, if this read has the crossbar's minimizer, then it writes it into its FIFO. Okay, so this is how we're doing the seeding. Next, I'll talk about both of the steps, and then I'll separate them. So conventional realignment filtering and read alignment. The filtering is done by heuristics, which is just simple similarity checks. They check the read and the reference segment and just check if they are similar. And then they perform optimal complex dynamic programming algorithms. And they both require loading the relevant reference segments before the computation. What Dartbeam does, we use dynamic programming algorithms like rows. For the filtering, we're using a linear, which is conventional Wagner-Fisher algorithm. And for the read alignment, we're using the affine, which is a modified Fisher algorithm. So we'll start talking about the filter. As I said, in the filtering, we're using the linear Wagner-Fisher algorithm, which is a known algorithm. Assuming we have swings S1 and S2, we construct the WF distance matrix. We initialize the first row and column, and then we fill the matrix D, where each cell, to calculate each cell, we need the top left, and left cells in order to compute it. Also, we are using blended metrics. How can we do it? We are using something that is called error threshold, which is the number of allowed differences between a read and a reference segment. Then we know that if we look at the main diagonal, and if we're going farther than the error threshold, then we know that we got a read and a reference, which are two different. So we know that we don't need to compute them, all the cells that are farther from the main diagonal. So in our case, if the error threshold is 6, which is a common value, we need to compute only 13 distances per row. Okay, how do we map this algorithm into a single row of the crossbar? Because I said we want to do it in a single crossbar row. The distance is 3 bits. The read length is 300 bits. The reference segment length is 600 bits. And the W distance buffer, it has 13 cells, one for each distance. Each one of them is 3 bits, so it's a total of 39 bits. And how can we do it? Because, as I said, each cell to compute it, okay, I'll show it here. Each cell, if I want to compute this cell, I need only the top left, and left cells. So I don't need everything that was before that. I need only them in order to compute it. So I can save only one row of the memory of the metrics at any certain time. Okay, and also the intermediate computation has 85 bits. Now let's see how I compute it. For example, I want to compute B1. So I need the value that is on the left, the value that is on the right, inside the row. This is the row in the middle. And the value that was initially there. And then after I compute it, I don't need the old value anymore. I can erase it and put the new value. And this is how I continue. So at any certain moment, I have only one row from the matrix. Okay, next, the read alignment. And as I said, it's also the Wagner-Fisher algorithm, but it's a modified one with the affine gap penalty, which takes into account the cost for opening a gap and also the cost for extending a gap. So again, if we take two strings, we construct the matrices, but this time we have 3 matrices instead of the one matrix that we had for the linear affine buffer, affine algorithm. And so it's much more complex. Okay, if we look at the entire remapping process of this is a crossbar of minimizer I. First, we do the indexing. We get the reference segment of minimizer I into the linear WF buffer. So we have all the reference segments that we need. And this is done offline. During runtime, we do the seeding, meaning that we enter the reads FIFO, the relevant reads with minimizer I. Then we perform the filtering. We take read J, we copy it to all of the rows, and then we execute in parallel all the distances. Then serially we compute the global minimum and find which one is the minimal, got the minimal distance. And this one is the one that continues with us to the next stage. And then we copy it to the affine buffer. So this is we got rid of all the others and we're left only with the best one from the previous stage. We do the same thing for more reads, and then when we don't have the space anymore in the affine buffer, then we compute also the affine calculation. And we send the results to the RISC-V, which manages it.
So you treat all types of errors the same? Substitution, insertion, and deletion?
That depends on the value of the algorithm. Oh, yeah. No, I have different, I can define different value and then it will have a different, I can treat them different. But in my case, in my results, I treat them the same. Okay. And we'll see that it's enough. We can improve it, but it's enough. So if we get,
Depends on the sequence of the machine.
yeah, for what we use the Illumina reads with 150 bases. It was enough for them, and they have a small amount of errors. So it's okay. So afterwards, when we get the read J, I just wanted to show that it's not calculated. Before I showed you just one crossbar, but for the same read, it's calculated in different crossbars with different minimizers. And then at the end, after we finish all the calculations, we need to take all of them and to find which is the minimum of them. And that's the RISC-V. Okay, and how do we evaluate our results? We compared to 5 state-of-the-art mappers. First one is Minimap is a CPU-based mapper, and NVIDIA PowerBricks is the GPU-based mapper. GenAsm and SIGRAM are a 3D stack memory accelerator, where SIGRAM is an improvement of GenAsm. And GenVom is an accelerator that is based on associative memristive memory. But they are using heuristics, so they improve the throughput and the area and everything, but at the cost of accuracy. How we evaluated our results, we built 4 simulators. The first one is a full system simulator, which is a C++ simulator that emulates the entire system. We had a single crossbar simulator that is a MATLAB simulator that models a single crossbar that operates cycle by cycle, and we showed that that in a single crossbar everything works correctly. We had a RISC-V simulator that is a Gen 5 based simulator for all the RISC-V cores. And we also implemented the controllers and synthesized them using a synopsis targeting this TSMC 25 nanometer CMC technology. So if we look at the graph that compares the accuracy with the throughput, we can see
How do you define accuracy?
how many locations for each read, how many for all of the reads, how many reads we map to the right locations compared to DWA.
Compared to some industry standard.
So we can see the GenVom has the best throughput, but comparable, I'll talk on our work in a second, comparable to our work, but it has much lower accuracy. And all the others have better accuracy. These are the mappers that are used today in the industry. This is the GPU based, this is the CPU based. And you can see that ours, it's a parameter that we define. And I didn't go into it in the scope, but you can see it in the paper. And you can see that.
Can you say in one sentence what are the numbers?
Yeah, it's the max, it's called the max reads, which limits the number of reads that I enter into a single crossbar. And I need this limit because there are some minimizers that appear many times in the reads, but then this minimizer doesn't have it doesn't add much information because it appears like many times. But then what happens is that when I entered the reads, there were crossbars that had many reads, and then when I finished with all of the crossbars, there were a few that kept computing only one crossbar. The thing is that I want to have all of the crosswords that are working together in order to improve the throughput. So this is the number of reads that I enter into a crossbar before I stop it. This is this value. Okay, is it clear? Okay, if I compare to state of the art, you can see the throughput, energy efficiency, and area efficiency of all of the works. And you can see that Genvom, the one that did the heuristics that got a better accuracy, they got the best results in all, but as I said, accuracy is bad. And all of the others that have a comparable accuracy, then we have a better throughput and better energy efficiency, and also area efficiency is quite similar to this one. So to conclude, Dark Theme is a novel framework for performing the entire read mapping process using the theme. All stages are performed within the same physical crossbars, and it eliminates the data transfer, and it achieves a significant improvement both the speed up and the energy efficiency compared to state of the art. Thank you. For the question, I want to say thank you to everyone in the group. It was very fun to work with you and work together. Thanks, Shaka, for everything. Ronnie, for your help. Ilana, Ilan, everyone. Ivan.
Which one?
Questions?
It seems that you provision the architecture for some specific reference. What if it changes and
If
you
it
need
changes-
more and you're stuck?
Yeah, so if it changes, you need to change the indexing step, which is done offline.
No, even the sizes.
But the sizes is it's good for a human genome or something similar. If you use something much smaller, like I don't know.
No, I don't mean the size, I mean the character, the similarities.
If
It
it's
may
the-
change.
Yeah, if it's the same size to human genome, then it's okay. You do the indexing stage again, which is done offline, so it's okay. You do it once. You divide the reference segments into the crossbars, and then you can do it. You can use it the same. Maybe some of the crossbars will be left empty, but it's okay.
Or you overload.
Yeah, it might happen, but I think that human genome is quite.
But you can change the algorithms and with the same architecture principles, right? If we change mostly the parameters.
No, but
No,
so
the number
is more
of
crossbars.
risk
I understand.
factors.
So it's a matter of control. It's not like changing the structure or the principle. We're changing
But
the
maybe we need
control.
more crossbars, but also we can put two minimizers in the same crossbar, and it's also possible. And then it's all only changing the control, but it's not changing the
Or
size.
you need more risk files, of course, because you're more rare.
It's a, yeah, that's a parameter that I can define. I can choose how many I'm going to use, how many. So that's, I can control.
I mean, you can think about the more modular architecture. This is something that you have redundancy, you support multiple operations, so you have redundant risk by code.
Anything else? Okay, thank you.